Welcome. This title of this presentation, Managing Demand Spikes in a Highly Flexible and Agile Deployment, is the award for the bullshit bingo today. Okay, let's go. As you see, let's start with myself. My name is Jan. I work for Midokura. I don't know if you ever heard of them. It's a company based in Tokyo, but also has some offices in San Francisco and Spain. And the second speaker on this slide, the first one is Masato from S2, which is a customer of Midokura and SUSE, who unfortunately couldn't make it here today, so I'm alone here. Let's switch to the agenda. I will give you a short introduction of these two companies, S2 and Midokura, why S2 did choose SUSE OpenStack with MidoNet, which MidoNet is a product of Midokura. I will give you the details about that in this presentation. Yeah, a MidoNet introduction and some use cases of S2. Some further resources if you want to find out more by yourself, and at the end some Q&A, time for Q&A. I'm not the original presenter for this. This was submitted by a colleague of mine who unfortunately left us. So bear with me, I'm not 100% the right one to do this presentation, but I will do it. Company introduction. S2 is basically a hosting provider in Japan. I don't know, I see at least one Japanese person here because I know him, but the others of you probably don't know much about Japan in terms of IT technology and stuff. Of course, Japan has a big IT industry. That's a bit one thing special about S2. I mean, they're basically a hosting provider, data centers, cloud services, managed services, the standard things. What is a bit special about them, if you look at Japan as a country and industry, in IT industry, 90% of Japanese IT business is based in Tokyo, which is the center. Also in general, I don't know how many million people live there. I would say like 80%, probably 70-80% of IT business is happening in Tokyo. But S2 is located in the northern east part of Japan. That's, if I say that word Fukushima, you know the place basically, I mean in this area. So they are a bit special. They on purpose, or they decided not to do their business in Tokyo like all the others, although it would probably be easier for them. But they decided, no, we stay in Tohoku, that's this region, it's called Tohoku, because they want to also, how to say that in English? I mean, support this area, let's call it like this. So they run their whole business in some area which is not that, doesn't have that high population, or it's a bit not a big city kind of thing. You will see more about what they do later in the use case section. The company I work for is called Midokura, and we do software engineering and services, mainly software-defined networking. In OpenStack terms, that means Neutron. So we have a Neutron plugin. It's called, the software is called MidoNet, which works as a Neutron plugin and replaces the default OVS plugin. Yeah, it integrates with OpenStack. I mean, you can run it standalone if you want, but 99% of our users use it with OpenStack. And additionally, we offer support and training for both OpenStack as it is and MidoNet, of course. Let me just ask a short question. I guess you all know about OpenStack and technical people. Yeah, you know Neutron. Okay, so I don't want to go too much into details there. Why did S2 choose SUSE with MidoNet? I mean, the first thing is they tried to run an OpenStack Cloud first they just tried different things. They tried Red Hat, they tried Ubuntu, they tried SUSE, and the decision to use SUSE OpenStack was because it just worked fast and easily compared to other solutions. Nevertheless, they have some special, not very special, but they have some demand for high availability and what's it called? I'm not a native English speaker, but whatever, they choose SUSE OpenStack with MidoNet for the ease of use, and they wanted to reduce the complexity that they have with that you have with the standard OVS plugin in Neutron. They want to have it scalable easily and fault tolerant, and open source technology. I mean, SUSE, you know, it is open source like most of the Linux distributions. The same is true for MidoNet, but on the other hand, they also need like a 24/7 commercial support. So if something breaks, they need someone to talk to that can help them troubleshoot and fix the issues. In MidoNet, I don't go into the details of SUSE. I guess you all know SUSE Cloud. I just assume that. MidoNet itself is open source. It's under the Apache 2 license. You can get it on GitHub if you want. There's installer packages, DEP, RPM, so you can just, if you want, use it on your own and be happy. Or if you want it with custom, commercial support, you can get a support contract with Midokura and get the same software, but with additional service and support options. What does MidoNet do? It is a software-defined network, so it virtualizes the cloud network and infrastructure on top of standard x86 hardware servers. It has virtual L2 and L3 distributed switching and routing and tenant isolation. On top of that, there are level 4 services like load balancer, firewall, or VPN functions. That's still, you get that with other competitors too, but that's what it does. If you want to program it yourself or what's it called? Operate it, not manually, there's a RESTful API where you can integrate that into scripts or custom tools or whatever you use. Oops. Yeah, that's MidoNet, the open source one, and what we offer is the Midokura Enterprise MidoNet, MEM, which is basically the same software with some additions. Top of it, the commercial support. So if you run into an issue, we have 24-hour support staff in America, in Europe, and in Japan to cover 24 hours a day. We offer a browser-based GUI for some advanced functions that you don't have within Horizon. And we offer something that we call Insights, which allows you to look or troubleshoot the SDN network itself. So if you have a connectivity issue between two VMs, for example, or two routers or something inside the virtual environment, you cannot usually do a whatever TCP dump on some hardware to look what's going on. For that, MEM offers some browser-based tool where you can trace connections, where you can have a flow history. You can go back like in time and see, filter by IP address or protocol or whatever, and see the flow history to see what worked or what probably failed. Also including some reporting functions where you can filter by tenant, for example, or by other components, and to see how much traffic went through a device, or how much traffic did a tenant generate in a certain time frame and stuff like that. Fabric, that's currently a beta feature which just has been released recently, and it's just a kind of technical preview state. That's a thing where if you use Cumulus-based switching hardware. You can install a piece of software on that lets you also analyze the underlay network. So if you have, for example, a switch that fails, a port is broken, or that's something you can easily find out with the other tools too. But let's say a connection is slow or whatever, this allows you to automatically look what's going on the underlay devices and where there may be problems. And another topic is VMware vSphere integration, where I don't go into the details today, but that's just something that our customers that are running vSphere at the moment, but they want to migrate to OpenStack, which is not that easy, but there's a tool that allows you to run vSphere and OpenStack together and migrate stuff over slowly. That's a basic overview about MidoNet and MidoNet, Midokura Enterprise MidoNet. If you have any questions, just raise your hand. We're a small group here, and I probably, if I continue like this, I'm done in 30 minutes. Feel free. I like this discussion style thing. I'm not very good at presenting. But what it's about actually the S2 use cases. That's the more interesting part. There are a few. Avoiding a single point of failure. If you have the standard OVS neutron deployment, you have the so-called network node, which handles a lot of your virtual network processing, and if that node fails, your cloud is offline, and that's something to avoid. Another thing is scaling north-south traffic. So that's also the network node in the end. So if you start with a small cloud, let's say 10 compute hosts or whatever, and you grow, you need more uplink capacity sooner or later. And then you can easily scale these by adding gateway nodes. You will see the technical implementation later in this presentation. Another use case for S2, they provide services for different types of companies, advertising agencies, normal people that just run some VMs, or smaller companies that use the public cloud, but also critical infrastructure, for example, financial institutions, banks. They require their own uplink, their own internet, or it's kind of one intranet, I mean private company external network connectivity. So that's a very interesting point, to easily separate these external connections by tenant. They run multiple data centers in different locations in Japan, and they also want to connect these. That means you run multiple OpenStack installations that are all separate from each other, but you connect these together and virtually have a single network that runs on both or multiple sites. Some other features are internal BGP. So if you have multiple tenants, networks, and you want to interconnect these, you don't have to do that via static routing. So there's no admin sitting there adding a route here or fiddling around something there. You can set that up via BGP. And these tenant routers will exchange this routing information automatically and allow you to have connectivity between different tenants. Another thing is VPN-as-a-Service, either for internal connectivity for security reasons, even if it's in the same cloud environment or data center. Customers want to avoid that even the admin or whatever could sniff some traffic. The second last point, L2 integration, that's via VTEP, that's VXLAN protocol. You can connect existing physical hardware servers, networks, with the virtual network in the same L2 segment. And yeah, this what I mentioned before, fabric troubleshooting, that's the troubleshooting of the underlying hardware, the underlay switches. I will now go through these topics one by one. The first one is avoiding the single point of failure. So this bottleneck network node, with MidoNet, you don't have that. In MidoNet, everything is distributed. The architecture is designed to be distributed. And you don't have a single network node, which, for example, has hundreds of DHCP namespaces or router namespaces running on it. And if it fails, the whole cloud is affected. We call that intelligence at the edge. That means the edge means that where the packet comes in or goes out, it is processed and calculated where it should go and what should happen with it. For example, you don't send the package from A to B to just find out that at B it gets dropped by a security guru. So you find that out at A. The whole simulation of the whole flow happens at the place where the packet starts, and depending on the outcome of the simulation, it's either dropped because it's not allowed, or it's sent to the target, to the destination host via a tunnel on the underlay. So that includes metadata in DHCP. So we don't run the DHCP and metadata agents that you have in standard Neutron installation. Instead, we have a so-called MidoNet agent. It's the same agent you run on compute hosts, on gateway hosts, on all hosts. It's the same software. And it immediately replies. For example, if you start a VM, it gets the DHCP and metadata from that host you run it on, from the compute host. The same is with security groups. Firewall rules, for example, don't get evaluated at the target of the connection, but at the source. If the packet will be dropped, theoretically at the target, it is physically dropped at the source. Why send it over the wire if it's going to be dropped? Analog for firewall and load balancing services. This is all calculated and decided at the source of the connection. In this slide, you see a comparison or like a graph of the physical network topology versus the Open vSwitch plugin versus MidoNet. On the left side, that's a standard graphic. You have a router, you have a switch, and some servers that run VMs on it, compute hosts. If you use that with the Neutron OVS plugin, you have this OVS agent on the compute hosts and on the network node, and additionally on the network node you have DHCP agent, L3 agent, metadata agent. In MidoNet you don't have that network node. You only have the MidoNet agent on the compute hosts, and it contains the logic that usually is done on the network node. So if you look at the packet flow in the physical environment, it goes from VM through the compute server to some router and goes back to the other server. Similar in case of the OVS plugin, it goes to the network node, and the network node sends it back to the target compute host. On the MidoNet case, it's different. The MidoNet agent on the first compute host simulates this packet. I mean, it has a virtual picture of the whole topology, and it knows, I mean, it calculates the target. So VM1 sends a packet to VM2, and if it's on the same server, it just sends it there. I mean, it doesn't leave this server. Or if it's on a different compute server, it will send it directly to that machine via a tunnel connection between these boxes. So there is no network node, or in the physical case, no router that breaks and you lose the connection. That's what we call intelligence at the edge. So the decision is made at the edge where the packet evolves, it's not transferred to a target if not necessary, only if it actually should go there. And a hardware failure has only partial impact. Of course, if some compute host fails, I mean the hard disk or whatever, the box dies, you can help with that. The software cannot fix that. But this affects only part of the cloud. And the same is what we call the gateway nodes. That's similar to the network node, but it doesn't have this intelligence. The gateway nodes are only the connection to the outside world. And of course, if that fails, the connection will not work anymore. But for redundancy, you use 2 of these boxes or even more and can avoid these failure and leaving your cloud online. So this is a similar picture to that one before. You have these agents on the top, the OVS case, you have these agents running on all the computes, the OVS agent, and on the network node, the DHCP and L3 agents. In the MidoNet case, this is about firewall. The logic of firewall and DHCP is done on the network node. In the MidoNet case, it's distributed. It's happening on the node where a packet originates. Another case is the scaling of north-south traffic. Yeah, that means you need more external bandwidth. You get more users, they use the internet or whatever you call that. You need more bandwidth and need to add that easily without having to configure a lot of stuff. And you don't want to have downtime. So what we do, we have this so-called gateway nodes. In the physical view, these are external routers. In this case, we have 2 that are connected to the internet or somewhere. And you have these server 1 and server 2. These are the gateway nodes. These run the MidoNet agent and connect to some uplink router via BGP protocol. In the lower pass, lower end, you have the internal, what's that called, the compute nodes running the VMs. Virtually, it looks like on the right side, so you have a tenant network and tenant router, that's the usual thing, and you have an external network. And then we have a thing called edge router. This edge router is a virtual router that connects to the physical upstream routers via BGP. So what it actually does on this edge router, you configure this BGP connection parameters, AES number and routing information. And this edge router is bound to the physical interfaces of these on the left side on server 1 and server 2. So server 1 and server 2 both have a NIC inside with a cable that connects them to the external world. And the edge router is a virtual router that has a neutron port on it, and that port is bound to the physical NIC and speaks BGP on that NIC. So what happens if, oh, it was fast, I don't have that slide. So what happens, for example, you have these 2 links, 2 routers, external 1 and external 2. They both use the same AES. And let's say router 1 dies. What will happen? The MidoNet agent will find out that the BGP connection died. They have some heartbeat, let's call it heartbeat mechanism, and it finds out, oh, router 1 is dead. And it automatically, BGP then automatically updates the routing information and everything gets sent out via router 2. And you fix router 1, and BGP automatically handles that you get the routing information for 1 back, and it uses both again. It's very simple, very simple and very easy for the administrator or operator. You don't have to manually delete the route, for example. Router 1 is not reachable anymore, but if you still would have the route to it, packets would be sent there and go to Nirvana. And by using BGP, this is all handled automatically. Similar topic is like in the standard case, you have like usually two gateway nodes because you want to have this redundancy. If one of them dies, it just switches over to the second one. But as I said before, for some customers, they want to have their own dedicated uplink. Usually for security reasons, but also probably for billing reasons for the cloud operator. Or for non-internet connectivity. The standard cloud is connected to the internet via multiple uplinks that are logically a single one. But some customers, they don't even have internet connectivity, but they have some other external network, some private network, but it's external to the cloud. And you don't want to handle that on the same physical box for several reasons. So what you do then, this is the standard common case. So you have two gateway hosts that connect to external world. You have a so-called uplink network. That's a special network type in Neutron. You can create that. I don't know if it's available in Horizon. Probably in the latest release it is. Else you can use the Neutron CLI. It's a special MidoNet type of network, which basically just defines the network. It's a point-to-point connection basically between the virtual edge router and the physical host. So it's the connection used to speak BGP. And below the edge router, you have what you all know, the external network in Neutron and Tenant routers that go down to the VMs. So if in this example, there's two gateway hosts. You should always have two because if one fails, you will still be online. And depending on the customer that uses the cloud, the big corporations or companies that have a lot of traffic, they have multiple gateway hosts. I mean, they have 3, 4, or 5, depending on what is needed. In this example, it's only 2. So what you do if you want to separate that between tenants, you just create another edge router. In this case, on the right side, you have a single edge router, a single tenant that has its private uplink. So it's 2, 3 Neutron commands to create that router, and of course, another gateway host that is dedicated to that one single tenant. The next use case is multi-site connectivity. That means basically connecting data centers and multiple OpenStack installations, but having single or multiple single networks on top of it. It uses VXLAN protocol, so the connection between these sites uses VXLAN tunneling, and the virtual routers, the endpoints on each data center, act as a VTEP virtual tunnel endpoint. This is how that looks like. Site A, site B, you have the usual topology, and they are usually connected to the internet, but there is a private wide access network that you use to interconnect those. And these routers, the green one and the red one, these are tenant routers, not red, the green and blue ones, these are tenant routers, and you configure them as VTEP endpoints, and they connect to each other. Oops, I'm not good at this. Yeah, and they connect to each other via this private network. And this is a bit more technical slide. So what happens on the router? They keep. I'm not sure how to say that. They in VXLAN, if you run a VTEP, of course these routers know about their local ports or local connected hosts and other devices and MAC addresses. They don't know about those on the other side directly. I mean, there's no ARP functioning between these hosts. So they keep a so-called MAC VTEP table. That means they talk to each other via VXLAN and exchange MAC address and IP address information from the other side. So I'm router A, and router B tells me I have this MAC address list. This is reachable via me, and the other way around. So these routers have their own MAC address list for the local side, and they have a remote MAC address list from the connected router, and so they know if a client requests a certain MAC address, they have to send it to the other router, which may be located in a different data center. So virtually, this looks like an L2 topology, but actually it uses layer 3 behind it and VXLAN tunnel on top of it. Another use case is internal BGP. So we had the BGP already for the external gateway for the north-south traffic, but sometimes you want to have that also for internal, inside the cloud, BGP between several tenants. So these tenant routers can exchange their routes. You don't have to do that manually. They use BGP to do that. And you can auto-connect these networks. Or of course you have to once set it up and tell them do iBGP, but after that they do it on their own. This is a simple graphic shown there. You have 3 routers ABC with VMs A, B, and C in different networks. So they have, in this start case, no non-local routes. And for example, you cannot connect from VMA to VMB or from VMA to VMC. But you can, that's actually not quite. Oh, you can, yeah, that's right. You cannot connect from A to B. There are 2 routers in the way that are not connected yet. You cannot connect from A to C, but you can connect from B to C. They have a single router that knows the direct routing information. So what you can do now, if you configure iBGP on that, these router A and B in this example exchange their routing information, and suddenly VMA can reach VMB. So the router A knows if you want to reach VMB, I have to send it to router B. And the same thing for the next step. So you have 2 BGP connections between these 3 routers, and they are all, it hops from A to B to C if you want to go from A to C. It's a very interesting thing. VPN-as-a-Service, that's also available in standard Neutron with other plugins. It's used to secure connections. You can use it also between private networks inside the cloud. You can use it between data centers. You can use it to connect to some other gateway and IPSec gateway outside the cloud. The technical implementation, it uses it's now called Libre S1. It was Open S1 or Free S1. I don't know, there are too many S1s nowadays. We use Libre S1. So the MidoNet agent just programs Open S1 with the necessary IPSec and IKEY policies. These are configured on a router, so you have 2 routers, A and B, and create a so-called VPN service on them, which knows the encryption options and whatever is needed to set up an IPSec connection. And then these guys talk IPSec or tunnel the traffic in IPSec between each other. This graphic shows, for example, on host 3, it's a compute host running 3 VMs, ABC, which 3 networks. We call them bridges internally. This is why it's written bridge A, B, and C. and routers. But it shows that, for example, the actual VPN service, LibreS1, is not running on that compute host. So, for example, VPN A and B are running on host 1, but VPN C is running on a different host. So you can control where to run these LibreS1 services. So they don't have to be on a compute host, for example. You can have them separated if you want. And the whole traffic handling, I didn't explain it yet. Middleman, I don't know, there's some, for American people it sounded weird. I was told it's some lady hygiene product or whatever. I don't know. Middleman is the MidoNet agent. That's this piece of software that you install in a MidoNet environment. So
middleman is considered an attack here.
An attack?
And a middleman, for example, if I was trying to communicate with him, a middleman attack would be him intercepting our conversation.
Ah, yeah, that's a different, still a different one. Okay. No, it's not attacking this one. Something you probably all heard of before is hardware L2 VTEP. That means you connect physical network and virtual network into a single L2 segment. So you have an existing old style, a non-cloud network with servers or whatever running, and you switch to the cloud and you cannot move your whole stuff to the cloud at once. So you want to move part of it one by one into the cloud, but keep them in the same segment. And you can do that with VTEP, that we heard that word before. It's also VXLAN. It's the same technology that was used in the slides before to interconnect between different sites. It maps physical ports to logical networks, and you set it up so the physical switches know how to reach the virtual machines in the cloud and the other way around. In our case, we support running this on a bunch of hardware switches by a few makers, basically running everything that runs Cumulus Linux should be working fine. So you have these boxes with Cumulus Linux, and behind them you have a bunch of servers. There's a lot of software, well, not a lot of software, but there's some software running on these Cumulus boxes. You all know Cumulus? Yes, no? Cumulus is basically a Debian-based switch operating system. It's a Debian. It's a Linux box with a standard Debian package management and everything. But they have this so-called switch D. So there's a driver for the switch. It's a chipset driver, hardware driver, and there's switch D, which is a Cumulus software running on top of Debian that does the calculation. I mean, that it contains the logic to handle routing information and stuff. And on the other side, you have your OpenStack installation, and you connect them via a VXLAN tunnel. That's what in the middle is. And the MidoNet has we call it the MidoNet cluster. It's a piece of logic in MidoNet that handles this VXLAN protocol and stores this information that's exchanged. So MidoNet talks to the OVSDB server on the switch and exchanges MAC address tables, basically, to put it into very simple words. And then these guys can talk to each other. It's the same as this site-to-site connection, just not inside a virtual topology, but with a physical hardware. So you can move boxes from your physical environment into the cloud without having to redesign your network or do some very strange or difficult routing exceptions and stuff. You just keep it as it is, as virtually a single level L2 environment. Yes, that's what it says. So you have the same subnet. You use the same subnet on both the physical and the virtual side. Fabric troubleshooting, I said that before. Unfortunately, I cannot show it to you now. I mean, I would really have loved to show you a visual demo, but it's just a tech preview. No one is really using that at the moment. I mean, not on the production systems. It requires you also to run cumulus switches because we install a piece of software on that checks the physical condition of the switch, of single ports, or of port congestion and stuff like that. A lot of information you can get out of that. And then this information can be visualized, and you can see it in your web browser. So you have it's usually only used for troubleshooting, but you have some connectivity issues inside your virtual environment, and you have no idea where it is. And then you can open the browser and you see a topology, the physical topology, switches and stuff. And the end goal, once that gets into production level, is that you, for example, can see the connections between ports and everything, and it's all green, except that one line is red, which means the port's either offline for whatever reason, or it's busy, or there's too much traffic, it's dropping packets because it can't handle them. So, and in the browser you have that integrated both, virtual and physical topologies. That's basically about the content of this presentation. If you need further information, the thing is called MidoNet. If you search for MidoNet on Google, you will find whatever you need to. You find all that. It's on GitHub. There's a wiki, there's a Slack channel for if you want to talk to some developers or whatever, some mailing lists, and an IRC channel to get in contact with MidoNet people. MidoNet.org is the homepage. There's a documentation site with installation guides and operation guide and technical documents about implementation and stuff. And if you want to see, the company is called Midokura. Actually, I didn't mention that in the beginning. Midokura was founded in 2010, like six and a half years ago. The original thing they wanted to do at that time was software-defined storage, but that for whatever reason that changed to software-defined network. And MidoNet was a closed source software until 2014, maybe around 2 years ago. Was made open source, Apache license, and yeah, that's where you can find some more information. That's it from my side. If you have any questions.